All right, a nice little introduction to Calc 1, the limit of a function. That's a little bit of a song called Windy and Warm. And it is really windy and warm today. As I'm recording this, feels like it's 100 degrees outside. All right, so we're going to go ahead and begin talking about the limit of a function. All right, so the lesson begins with talking about what's called Zenos Paradox, okay? If you're a football fan, I kind of use this example sometimes. If a team is like close to the goal line when there's a penalty, it's usually half the distance to the goal. So the idea would be if the defense just kept having penalties over and over again, like jumping off sides, you would keep going half the distance to the goal. So the question is, would the football ever reach the goal line or not? It would just get, infinitesimally closer. This idea of Zenos Paradox, goes back to the Greek civilization, I believe. This shows this, and it's kind of an interesting idea on this. So the idea is if you're going to go from this point to this point, like on a basketball court, well, the only way to get not the only way, but one way to get there is to go halfway. So now we're 50% to the end. Then we go halfway again. So now we're 75%. Then we go half this distance again, 87.5%. Then half the distance again. And if you see right now, we're 93.75%. So if we keep going half this distance, the question is, well, in the mathematical world, will we ever make it to 100%? In the mathematical world, the answer is no. This thing will just keep getting closer and closer to 100%, and because the decimals go out, 99.99, remember the decimals go on forever, so I think on this little applet, the furthest I'm ever going to get is like this, and then, well, we did make it to 100%, but that's not the reality, okay? So, that's a paradox, and the idea behind this is if you keep going half a distance, then you really never make it to 100%. All right, that's just because this computer is not powerful enough to go out any further decimals. All right, well, the idea in calculus of a limit really, solves that paradox. We didn't have calculus back in the Greek civilization, but some of the ideas were kind of there. Some of the primitive ideas were. So to begin with, what I'm going to have you do is we're going to graph this function, and that's a line. So hopefully you got pretty good knowledge from your background of lines. Remember, this is the slope, and this is the y-intercept. So you can go ahead and graph that. So the way we'd do that is we'd just put a dot on the y-intercept at -4. We have a slope of 3 over 1. We're just going up 3, and we're going to the right 1. So I'm going to go from the intercept up 3, right 1, repeat that a few times, and then what I'll do is I'll just sketch in that line, and then we're going to do something on our calculator to begin to develop this idea of a limit, okay? All right, so what I'm going to do on this is you can get your calculator out, and this will demonstrate this pretty well. So I can put in, go to y equals, put in 3x minus 4, and then we're going to graph in a standard window. If you're not real familiar with this, the simplest way to graph in a standard window, going -10 to 10, is just go zoom number 6. Okay, so that's our line like that. Okay, what we're going to do is we're going to trace on this. The idea on this essentially is going to be that we're interested in what's happening at x equals 2, We're interested in what's happening at this function at x equals 2. So we're going to use values that get closer and closer to 2 that are underneath 2 and above 2. Okay, so here's what I'm going to do on this. We're just going to trace this out. Trace 1.9, and that'll give 1.7. And we'll just kind of record those as we go. Now we get a little closer, kind of like on the Zenos Paradox idea I was showing you. So we do 1.99. That gives 1.97. Okay, and then we do, oh, there's my cursor, 1.999. That's getting even closer. And that's 1.997. So that number is getting close to something. What does it look like it's approaching? Yeah, doesn't it look like it's getting close to 2? Okay, all right. Let's go down here now. Let's use some numbers bigger. So 2.1, trace that. All right, now on that side, that gives 2.3. Okay, now we're closing in on 2 from the right. So we go 2.01. Let's see, that gives 2.03. Then we go 2.001. So that gives 2.003. Okay, and the idea on this essentially is this. This thing is going, looks like it's going to 2. And if you look at this thing also looks like it's closing in on 2. So when we're talking about a limit, we're really looking at where is this value of f of x going. So the notation on this is we would say the limit of 3x minus 4 as x approaches 2 is equal to some number. That number it's approaching when x goes to 2 looks like it's going towards 2. So you can, this methodology, you're just kind of looking at where it approaches. Now, the idea you might think is, why don't I just trace it 2? Well, if I trace it 2, of course I get 2. There's all kinds of different situations on these limits. In this case, yeah, the limit just turns out to be the function value. Just turns out to be when x is 2, y is 2, right? So a couple things I want to mention on here is when you're finding the value of a limit, you're looking at the answer is always a y value. So your answer to a limit is a y value, and you're looking at what it approaches. We'll kind of get away from doing these table of values, but this is a good way to start, okay? All right, so the next thing we'll look at is introduce you to the two-sided left-hand and right-hand limit notation. So a two-sided limit, you just have the arrow, x approaches a number. The left hand, you have x approaches a number, and then you have that superscript. What that means is you're going from the left, okay? Right-hand limit, you have x approaches a, and then you have the plus sign, the positive for a superscript. That means you're approaching from the right. The two-sided limit means you're doing the left and right at the same time. So if you look at this, this would be the left-hand limit right here. This left-hand limit would be approaching 2. The right hand would be you're going from the right of 2. That would also be 2 like that. Okay, so that's the idea. All right, I'm going to open up, let's see, maybe this. I think I got a couple of applets on here. I'm kind of a fan of applets. GeoGebra is a good website that's got lots of applets to show. So here's the idea on here. This is a function. This is a parabola. We're going to look at the limit as we approach 2 again. So what this is, this delta x just means right now I'm 1 unit to the right of 2. And I'm 1 unit to the left of 2. So the idea when you're doing a limit is you're looking at these y values as delta x gets closer and closer to 0. As you get closer to that 2, here's what happens. So watch these y values right there. And look at what they're approaching. Okay, so as we do this, you can see the red and green and purple band, they're approaching that value, that y value that's in red. And that y value is negative 2.8 on here. Right? So the right-hand limit is the green. Right? That right-hand limit is approaching the negative 2.8. The left-hand limit is the purple. it's also approaching that same function value, like that. And then the two-sided limit would be both of those things are coming towards the same place, so it's the same value. So that's the idea with this. And we're going to look at lots of different situations. Here's another situation I'm going to go ahead and show you. This is the graph of 1 over x minus 2. You actually have a vertical asymptote here. So what will happen is, let's look at the right-hand limit. Okay, the right-hand limit's in green. So watch the green bar. As I get closer to 2, what's happening to the y value? What's it doing? Look at that y, look at that green bar here. What's that doing? It's getting bigger and bigger infinitely. So that right-hand limit is going to infinity. Okay? The left-hand limit, which would be the purple, as we get closer to 2, look at what happens to the y value. So just watch that. Look at this kind of part right here. This part right here is getting closer and closer, just going towards negative infinity. So the left hand goes to negative infinity. The right hand goes to infinity. All right, now that in this case, we're going to learn that the two-sided limit, which is this part in red, does not exist. Okay, all right, so that'll kind of get us started on that a little bit. Then I'm going to run to the next page here. Okay, so let's go to the next page here, and we're going to graph this. We're going to use our calculator a lot on these problems, so go ahead and put this function in your calculator. We'll go x to the second minus 4. I hope you know from your background that's a parabola that's been switched down 4 units. You learned that in pre-calculus, college algebra. Again, we'll just go zoom 6 to get a basic standard window. And what we're going to do to get a good accurate graph, go to your table of values so you can go second graph and then just start plotting some of these points on here. So I'm just going to find some good points. Here's negative 2, 0. There's negative 1, negative 3, 0, negative 4, 1, negative 3, and 2, 0, and that's probably good enough. You also have 3, 5, and go ahead and put that on there. Negative 3, 5, and then go ahead and connect that into the quadratic function, the parabola. God, that's hard to do on this thing. Okay, so there's our graph. We're going to go ahead again and just fill in, trace out these values. So we're going to, this time what we're going to be interested in is what's happening when x is 1. We're interested in the limit when x is 1. All right, so let's just start tracing, and let's start recording these. First of all, I'm going to kind of go from the left here. So I'm going to trace at negative 1.1 and record what we have. So you want to go ahead and record. That's negative 2.79. Get a little closer to negative 1. So now we'll go negative 1.01. That'll give negative 2.9799. And then let's go closer, negative 1.001. And that's going to give negative 2.997999, like that. All right, so the idea is, what does it look like this number is getting closer to? As we get closer to negative 1, yeah, that looks like it's heading to negative 3, okay? So that would be the value of that left-hand limit. This right here is the left-hand limit, appears to be going to negative 3, okay? Now we're going to do the right-hand limit just by tracing the same way. So we're taking a number that's a little bit bigger than negative 1. So we're on the right side of that. So we're going to start with negative 0.9, and we'll record what that is. So that is negative 3.19. Go a little closer, negative 0.99. Negative 3.0199. And then one more time, negative 0.999. And then record that. So that's negative 3.001999. All right, so the right-hand limit is numbers coming from the right of negative 1. What does it look like these are going to? Yeah, that also looks like that's going to negative 3, doesn't it? Okay, so that's the idea. What's going to happen on this is, when you're looking at your graph, a good way to do this is just draw like this is kind of like a wall. It's like just a vertical line. The left-hand limit, when you're doing a left-hand limit, you're just going to go to the left, kind of trace out on the function until you get real close to that x value of -1. And then see, that's approaching that y value of -3. The right-hand limit, you just go to the right, like this, and you kind of close in, and when you get real close to that wall, you're also getting close to -3. So what you'd have is the right-hand limit would be -3, and then this is the two-sided limit right here. Well, it would also go to -3. Because the left and right are going to the same place, that's what you would have. It's kind of like just take your finger and trace, If your fingers come together, then that would be the value of your two-sided limit. Okay, so that's how that goes, right? All right, hopefully we're clear on that. All right, next thing we're going to do is we're going to move down and work on piece functions a little bit. Piecewise functions, sometimes students don't do so hot on piecewise functions. So we're going to crunch out a couple of tables of values. To me, this is the safe way to go about doing this. So just draw yourself a table of values. We're going to have x, and we're going to look at the first piece, which is defined to be this. So that's y equals 2x plus 3. Now what's important on this is we're not going to just use any x value we want. We're going to use values smaller than 1. We're going to go ahead and start at 1 because that's the end of the boundary. And since that's a less than, this is going to come to end at an open bubble. Okay, hopefully you've seen this a little bit in college algebra. Then we're just going to pick a couple of numbers smaller than 1, like say 0 and -1. It's a line, so all we really need is two points anyway. All right, so what we do is we just crunch this out. So we're going to plug in the x value into the function. So we'd have 2 times 1 plus 3 would be 5. 2 times 0 plus 3 would be 3. And 2 times -1 plus 3 would be 1. Okay? All right? So let's just plot those points. Now, when we plot 1, 5, going over 1 up 5, you want to put an open bubble. And then we got 0, 3. Then we got -1, 1. And then you want to go ahead and connect the dot. Now, this is real important on this. When you draw this line on here, you're not going to draw the line going in both directions. You're going to draw the line just going in that direction only. Okay, so that's pretty important that you understand that. Okay, so that's how that line goes. All right. Second thing we're going to do is we're going to do a different table of values for the other piece. The other piece is this part. Okay, so this goes like this. We have x and we have y equals 2x minus 3. All right, so we're going to start with 1. We're going to use values bigger than 1. Okay, since that has an equal to bar under it, that means that interval comes to an end at a solid dot. Okay, so that's what we call a closed interval. Okay, then we just plug in. So we got 2 times 1 minus 3, which is -1. 2 times 2 minus 3 would be 1. 2 times 3 minus 3 would be 3, and we're going to plot those points. So when we plot 1, -1, you want to use a solid dot. 2, 1, plot like that. 3, 3. And then again, when we do the graph of this, your line's only going to go to the right. So it's going to start here, and it's going to go off in that direction like that. Okay? So that's kind of what the way your point looks. All right? So again, we're going to use the calculator. We're going to eventually get away from doing the calculator. This is more conceptual, trying to get you establish the idea here. So this is what I'm going to do first of all, is I'm going to show you how to put these individual pieces in your calculator. Okay? So one thing that you want to look at is there's a button math test. If you go second math, you will find all these inequalities. Okay, so what I'm going to do is I'm going to put this part in yellow in. The way I do this on a graphing calculator is I go parentheses 2x plus 3, close the parenthesis. Then I use the division symbol as a separator. Then I go X. I got to go to math test. Whoops, so I got to go second math. Find the less than symbol, which is number 5. Then I put in the condition 1 and then close the parenthesis. All right, so that's how that goes. I'll try to put that over kind of at the side so you can refer to that. Then if you graph, well, it does that. It doesn't show the open bubble, so you have to know that's there, but it just graphs the piece of that. Okay, now what we're going to do is we're going to trace on our calculator. So I'm just going to start tracing out these values. So I'm going to trace at 0.9 and record like we've been doing. So that is 4.8. I'm going to trace at 0.99. So that's going to be 4.98. I'm going to trace at 0.999. So that's going to be 4.998, like that. All right. And again, what we're doing is we're going to be looking at the limit as we approach 1. So the left-hand limit is going to be this red part. We're coming from the left. So this part B would be the left-hand limit because of that negative superscript. What does it look like it's going to? Exactly. It looks like it's going to 5. Okay, very good. All right. So now what I'm going to do is we're going to do the right-hand limit. So what I'm going to do is I'm just going to erase this graph, right? And I'm going to start over again. I'm going to put the second piece in. So I go 2x minus 3. Okay, division symbol, parenthesis, x, test. And then now we're going to put in the greater than or equal to symbol, which is option 4. So we're going to do x greater than or equal to 1. Like that. Okay, we'll graph it. I'll put that to the side so you can, again, see what I did. And then we go ahead and graph that. Okay, so what I want to do now is we're going to trace these values here. Excuse me. So let's start at 1.1. Let's take your calculator and start tracing these things out and recording. So we got 1.1. And that gives negative 0.8. Do 1.01. That's a little closer to 1 from the right. So that's negative 0.98. And then 1.001. That's closer still. So that is negative 0.998. All right, so now we have just kind of asked the same question. Okay, what does it look like that's going to? Look, these numbers look like they're going towards, what do you think, negative 1? Okay, so this right-hand limit is heading towards negative 1. The left-hand limit is going towards 5. All right, you can see that pretty clearly on the graph. This thing right here is just heading towards that y value of 5. The right-hand limit, this part right here, is heading towards negative 1. Remember, the answer to a limit's a y value. So what we say in this case is the two-sided limit does not exist. So since these are not going to the same place, the two-sided limit does not exist. And you'll see me use the abbreviation DNE over and over again. You're more than welcome to just use that abbreviation when that happens. So the two-sided limit doesn't exist in that case. All right, so if you have a break in the graph, that's what happens, typically. Depends kind of on the situation. So the left and right-hand limit have different values. They can have that depending on how the function looks. Okay, so I'm going to move on. Remember, this is a video. You can pause anytime you want to. You can rewind, fast forward, whatever you want to do. Okay, it's you have the power. Unlike if you take, my class. I'm making this video mostly for online class, but if you take a class from me, well, you can ask questions and pause me, but you can't rewind me too much, okay? All right, so let's go ahead and let's move on to this, and this is another piecewise function. And again, what I'm going to do is we're going to do these two pieces. So we're going to do this, and we're going to make a table of values. The first table of values, we're going to use the square root of x. And again, we're going to use numbers 0 and bigger. We go ahead and start at 0. We make a note to ourselves that that's going to be a solid closed interval. That's because it has the equal to bar, so we include that. Then we're just going to pick numbers bigger than 0. But let's be smart about the way we do it. Let's use 1. Let's not use 2 because square root of 2 is a bunch of decimals. And let's go on to 4. We know what the square root of 4 is. And let's go to 9. I'm basically just picking numbers I know square roots of. You don't have to pick anything else. That's good enough. So we do the square root of 0, which is 0. The square root of 1 is 1. Square root of 4 is 2. And the square root of 9 is 3. Okay, and we'll go ahead and go down to our graph, and we'll go ahead and plot those points. So we have 0, 0, solid, 1, 1, 4, 2, and go out to 9, and then that's 9, 3. And then just connect your graph. Now this graph only goes to the right, okay? It just goes that way. Sometimes I see students want to make it go on. No, 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 no. We only are using x values bigger than 0, all right? So now we go to the second part here, and we're going to do this. So let's see. We're going to do y equals absolute value of x. And what I'm going to do on this then is we're going to pick numbers smaller than 0. Now we will pick 0. Remember, you got to pick that endpoint, but you realize that it's an open interval, okay? And that's because you don't have the equality bar under that. Then you pick numbers less than 0. So let's just pick some negative numbers. That's all good enough. And we're going to do the absolute value. So absolute value of 0 is 0. Absolute value of a negative number is a positive, and so forth. You can do all this in your head if you want to, of course, all right? So let's plot that. We have 0, 0. Now 0, 0 connects here. So you don't put an open bubble. You just realize, okay, we connected. Then we have negative 1, 1, negative 2, 2, negative 3, 3. And then we can sketch that line, okay? All right, so if we go through and sketch that line, that's what the graph looks like, is like that, okay? Now, we're not really doing the table of values with the decimals this time. We're going to kind of begin to get away from that. But we'll do something with this on the calculator in a minute. So let's just look, first of all, this one is the right-hand limit because it's got the plus sign. So what that means is get to the right of x equals 0. Here's where x is 0. And just kind of trace in, okay? As we're getting closer and closer and closer to 0, what is the y value getting close to? Yeah, the y value is getting close to 0. So that's the right-hand limit, okay? Now we'll do the left-hand limit. So this one is the left-hand limit. So what I'm going to do on this then is we just get to the left of 0 and we start closing in, okay? We're getting closer. Right now we have at 3, 2, 1. The y values are getting close to 0. All right, so that would be equal to 0. All right, what's the two-sided limit? This is the two-sided limit, so what would it be? Okay, it would also be 0. It's going to the same place. So anytime the left and right-hand limit are equal, then that will be the answer to the two-sided limit. The two-sided limit won't exist if the left and right are going to different places, okay? All right, so we're going to show you something on the calculator. I want to go ahead and do this piecewise function, show you how you do this. So we're going to do square root of x. So generally what you can do on this is just do square root. It kind of depends on your calculator. To be safe, you put that whole thing in parentheses. It just depends on what that function is. Always use a division bar, then do x greater than or equal to 0. Absolute value, you have a command. You have to go absx / and then you can go x less than 0. You can actually leave the parentheses off of this function unless it has more than one term in it, added or subtracted. All right, so the otherwise calculator needs to know what you're talking about. Okay, so put this in. Make sure you know how to do this. I'll erase this. First thing I do is I just go square root of x, like that. Do division symbol, parenthesis, x, test. So go second math. And we're going to put in the greater than or equal to 0. And then that'll give you that graph. Okay. put in ABS. Now ABS is here. You got to go math, number. Okay, ABS. So again, it's math, number, then ABS. Okay, put in absolute value of X, divide, and then put in the condition. Parenthesis, X, test, and this one is less than, so it's number 5, so less than 0. Okay, and that's it. So that's how that would be put in your calculator. I'll put this over here, so refer to it if you want to. The graph, that's what it looks like. Okay, now what'll happen on this is it won't show the bubbles and stuff, but it does pretty clearly show those two things connect. Now, one more time on this. Of course, now I'll show you how to trace on this. So if you were going to trace the left-hand limit, going from the left, you would go like this, trace. Then you would have to make sure that you're on the red graph. You aren't, so you have to kind of toggle down. Now you're ready to trace on it. Okay, so I'll show you kind of a neat way to do this. You can go negative, we can start like at -5. And then you can just go like this. See how I'm just doing the right? Now look at that, how that y values change. This is a real good way to see how limits are going. As we get close to 0, the y value is, you can tell it's getting close to 0. So you can do it like that, okay? If you want to trace on the right side, you go trace, make sure the blue graph is lined up, then just kind of pick a number like 5 or something, and then just go with your left cursor, just close in from the right. You can tell these y values are getting close to 0. So you can really understand the idea of limits real well if you take a little bit of time on your calculator. That's the way this stuff goes. Okay? All right, very good. All right, so the theorem then is this. This is basically what this problem was demonstrating. If the right-hand limit and the left-hand limit are equal, which they are here, notice the left-hand limit and right-hand limit were 0, then that's the answer to the two-sided limit. So it's just saying if the right hand is L, the left hand's L, then the two-sided, oops, I think I did the notation, I think I wrote something wrong on your guys' notes here. I need to be careful about that. So it goes like this, okay? This is the left hand, this is the right hand, and this is supposed to be the two-sided. Okay, so that's what was supposed to be. I apologize, I typed that wrong. So if the left and right are the same, then that's what the two-sided is. Okay, if the right and left approach different values, then the two-sided doesn't exist. So we saw those two examples in. All right, so I'm ready to move to page 4, and this will kind of be the end of the first part of the video I'm going to make. One more time with piecewise functions. So here's what I'm going to have you all do. And this is important too. I want you to pause the video. I've done enough work on this. I want you all to try this yourself. Please do this. Don't just move ahead and record what I do. See if you're processing this correctly. Make your table of values for your two functions. So you can use like this one as x plus 2. And you can use this one as y equals x squared minus 2. Do your graph. See if you can get that typed in your calculator just to make sure your graph looks right. And then do those limits. Okay, so I'll let you go ahead and start on that. When you're done, just resume the video. Okay, I kind of realized I made a mistake on this. I want you to just kind of see if you, first of all, make sure you got your graph right. Double check your table of values. This would be for x plus 2. That would be this line. There would be a bubble at 2, 4 because it's greater than 2. And this is your parabola, which would be the part that I have in red. You would use a solid dot at 2 like that. So you want to make sure you got your table right, and you want to make sure that your graph looks right. Okay, this is how this goes in the calculator, so hopefully that worked out okay for you, and you know how to do that. Now, I had these limits going to 0. That's not what I intended. If you were looking at the limits as you approach 0, well, this is what would happen here. So if you're going to the left, when x goes to 0, you're going to -2. So that left-hand limit would be -2. The right-hand limit, as you go to 0, would never make it there. Okay, okay, on the blue graph, that is. So you'd have to get on the red graph and close in like that. Well, that would make it to -2, and therefore the two-sided would be -2. Now, that's not what I intended. That's my fault on that. I intended these things to go to 2 because the graph's a little more interesting there. So this is kind of what I was after here. In this case, the left-hand limit would go to, it looks like that would go to 2. So this would be your left-hand limit, would be going to 2. And then your right-hand limit, which would be this part right here, that looks like that would be going to 4. And therefore the two-sided limit doesn't exist. Okay, so we're closing in on 2. And if you look at this table of values, see on this one of them goes to 4, one of them goes to 2. Okay, and that's the idea on that. Okay, so if you're coming from the right, you hit 4. If you're coming from the left, which is these numbers here, then you're going to head towards 2. So that's what I intended. Okay, all right, one more time. Pause the video if you need to pause and make any corrections. Otherwise, I'm going to move down and let you do one more problem. You don't have to do this one on the calculator. Just see what you get on this one then. Okay, and if you got these okay, then you should be in good shape. Okay, I made a similar mistake again. I figured out, I don't know why I did that. I guess I was cutting and pasting and forgot to change the 0. I meant to go to 1 like this. So the first thing to do is to make sure you got the same graph I got. Double check over that. Make sure your table of values are right. Make sure that you have the open and solid in the right place and that your graph looks fine. So what we have on this is the right-hand limit would be, if you're doing the right-hand limit, you would, and this is the way I sometimes students struggle catching on to this, and it's one way to do is just kind of draw a vertical bar. We're interested in the limit as we go to 1. That's what I intended. So the right-hand limit just goes like this. Okay, what is the function value approaching? It's approaching 5. So that right-hand limit would be 5. Okay, the left-hand limit would be like this. Okay, so we're just going from the left, going from the left, going from the left. As we get close to that bar, we're getting close to 1. Okay, so the value of that left-hand limit, which is this, would be going to 1. So what would you conclude about the two-sided? Yeah, that does not exist. So that's what I intended. Sorry about those last 2 problems. I can ask a limit at any value, but I usually am kind of looking at special places where there's a break or like a hole or something like that, where it's a little more interesting. Okay. All right, so that'll take care of the first part of the video. Hopefully that'll get you off to a good start. And I'll do this, this section's pretty long, so I'll do this in different parts. Good luck.